In this video, I'll be explaining to you how to do all the questions to do with exercise 704, questions 6 to 11 on direct linear variation. Let's start off with question 6. For an object that is cooling, the drop in temperature varies directly with time. If the temperature drops 8 degrees in 5 minutes, which of the following is the amount of time it would take for the temperature to drop 10 degrees? Well, we know first of all that the drop in temperature varies directly with time. So we can write an equation relating those two, which is capital T for temperature equals KT, where K is the proportionality constant. So if the temperature drops 8 degrees in 5 minutes, this means that the capital T is 8 degrees and the lowercase t is 5 minutes. So let's make a substitution. 8 would equal to K times 5. And so if we want to solve for K, we're going to divide both sides by 5, like so. And then we cancel out the times 5 and divided by 5. So K is basically 8 over 5, which we can then simplify to 1.6 as a decimal. Now, after we get K, we can substitute this back into our equation. So therefore, T would equal to 1.6 times lowercase t. And then we can start answering the rest of the question. So for the rest of the question, it says, which of the following is the amount of time it would take for the temperature to drop 10 degrees? So you want the degrees to be 10 to be dropped, and you want to find the time for which it will drop. So we'll make capital T 10. That's equal to 1.6 times lowercase t. And then what we can do is we divide both sides by 1.6, or just divide 1.6 over. So you get 10 over 1.6 equals t. And 10 over 1.6, well, that will give you 6.25. And the units is in minutes, so we're going to write minutes after that. Okay? There we go. And that's A. Moving on to question 7. Question 7 says the volume V liters of water in a tank that is filled is proportional to the time taken into minutes, as shown in the graph. So as time goes by, the volume of the water tank is going to go higher and higher and higher. It's getting filled by water. So find the constant variation, which is K. And before that, we need to construct our equation. So we know that this is to do with volume and time. So we're going to do volume equals K times lowercase t. And we have to make sure we substitute something to do with that. Okay? So we should find out a dot on this line that is on the corner of a grid, right? So the first value that I can see that is on the corner of a grid is right here. Okay? So I'm just going to use that point. And that point is basically 5, 320, where 5 belongs to T and 320 is V. So we're going to make sure we substitute that correctly. So the volume is 320 liters, whereas the time was 5 minutes when that was the volume. So we're now going to divide both sides by 5 to find out what's K. So we get K as the number 64. Okay? Then for question B, what does the constant you found in part A represent? So V equals to 64T, right? Now, this is basically your gradient of the line, okay? So this is the gradient of the line. And the gradient of the line is 64 in this case. And the gradient is always to do with two numbers, which is a rise over a run. So we're going to make the 64 to be put over 1. Now, this gradient here tells us that it's rising by 64 liters. Okay, so rise by 64 liters. Okay, and this is run, which is by 1 minute every single time. Okay, so this constant of variation tells me that the water is rising by 64 liters every minute. Okay? let's have a look at question C. Calculate the amount of water in the tank after 8 minutes. So we now have this formula, and the time is 8 minutes, so we're going to directly substitute that in here. So volume is 64 times 8, and that will tell us how much water there is in there after 8 minutes. So V equals to 512 litres of water in the tank. Question D. Calculate how long it takes to pump 960 litres of water into the tank. So now that number there indicates our volume in the tank, which means that we have to substitute that in here as V, and we're going to find the time, which is how long it takes. So instead of V, we're going to put 960 equal to 64T, and we'll divide that 64 over to the other side, so that 960 over 64 equals to T, and 960 divided by 64 will give you the number 15. And just by checking out the units here, T is in minutes, so we're going to say it takes 15 minutes to fill up 960 litres. Right, let's go on to the next question. Question 8. The distance travelled by a marathon runner varies directly with time. This makes sense, as the person running would run more distance, okay, as time goes by. Part A says if he covers 9.75 kilometres in 45 minutes, calculate how long it would take him to run 26 kilometres. So in this case, we need to find out a formula to do that. So D is equal to KT. Okay, so distance is very proportionally with time. And we're going to substitute in 9.75 as D, and then the time as 45 minutes. Okay? So 9.75 equals to K times 45. And then, well, what happens to K now, okay, is 9.75 must be divided by 45, and that will give you 1360. So K would equal to 9.75 over 45, which is now 13 over 60. And so if we substitute that back into the formula, we get D equals to 13 over 60 T. Okay? So once we've got that K value and our formula, we can now calculate the duration that would take him to run 26 kilometers. So we can substitute that as D right there. So 26 equals to 13 over 60 T. And just don't forget that there is the times there. So if we want to move this term over to the other side, then 26 will be divided by 13 over 60, okay, instead of multiplying, and that equals time. So 26 divided by this answer is going to give us 120, and this will be in minutes. Okay, or we can simply write this as 2 hours, since that's 2 lots of 60. Question B. What is the limitation of this linear model? So we know that as we graph this, okay, it's true, yeah, that as time goes by, distance increases. But can he run for, let's say, 10 hours or so? Can he run consistently? He wouldn't be able to, or she wouldn't be able to, because they need a rest. So the answer for this is the marathon runner cannot continue to run forever, and needs to rest. So it might be correct for maybe the first leg of the journey, and then he needs to rest, and then maybe it's true for the second leg of the journey, okay? And over time, he'll get tired anyway, or she'll get tired, so it's not realistic. Let's move on to question 9. The weight of an astronaut on Mars is proportional to his weight on Earth, meaning that the heavier he is on Earth, or she is on Earth, then the heavier they are on Mars. So a 72 kilogram astronaut weighs 27.4 kilograms on Mars. Calculate how much a 60 kilogram astronaut weighs on Mars, correct to one decimal place. So the two places that we're looking at are Mars and Earth. So we can say for question A, capital M for Mars is proportional to their weight on Earth. And we can make a substitution of 72 kilograms on Earth compared to 27.4 kilograms on Mars. So we're going to replace M by 27.4, the weight on Mars, equals K times 72. We'll divide 72 over to other side to find K, so that will be 27.4 over 72. Putting that on my calculator gets me 0.38 blah blah blah, keeps going. I wouldn't necessarily write 0.3805 like they have in the answers. I would write this as 137 over 360 and not round it. Okay, so this was actually 0.380, etc. Okay, so don't write this. I like you to write this instead because it's more accurate and it's not rounded. So now we can substitute that back in to our equation. We'll get M equals to 137 over 360 E. And what we have to do here is calculate how much a 60 kilogram astronaut weighs on Mars. So we're calculating M, whilst 60 kilograms is how much this person weighs on Earth. So let's make a substitution of 60. So if I make a substitution of 60, then that means M would equal to 22.83, so on. And so to the nearest one decimal place for this question, it would be 22.8 kilograms. Question B. If an astronaut weighs 32 kilograms on Mars, calculate his weight on Earth, correct to one decimal place. So let's write down our formula again, which is this. But the weight here is on Mars. So this is M. So we're going to replace M by that value, but then find out what the weight on Earth is. So let's replace M by 32. Write down the rest of the stuff here. And we're going to move this over to the other side, which means we divide both sides by this number. So 32 divided by 137 over 360 is equal to E. Okay, and what we'll get is E being 84.087 and so on forth. And so when we round this to one decimal place, we will get 84.1 kilograms. Okay, so that a person weighing 32 kilograms on Mars weighs 84.1 kilograms on Earth, which is heavier on Earth. Okay, let's move on. Question 10. Nick noticed that during his road trip, the amount of petrol used by his car varied with the amount of time that he drove. It consumed 45 litres of petrol in 4 hours. How long to the nearest minute will Nick's car take to consume 100 litres of petrol? So, there's amount of petrol that we have to look at, and time. So those are the two quantities that change over time. So we can say capital P for petrol equals to KT, okay, so K times time. It consumed 45 litres of petrol in 4 hours. So we can substitute in the amount of petrol as 45 and the time as 4. So 45 equals to K times 4, which means that dividing 4 over 45 over 4 equals K. So K will be equal to 11.25. Now if I put this back in the equation, this will be 11.25T. And this is the gradient that's relating the amount of petrol used per hour. Okay, so every hour, Nick would consume 11.25 litres of petrol from his car. So, how long to the nearest minute will Nick's car take to consume 100 litres of petrol? So we can make this number 100. So the 100 is now equal to 11.25t. We divide the 11.25 over. So that 100 divided by 11.25 will be 8.88 hours. But then if we press the degrees, minutes, seconds button, so it's this button here, okay, on the calculator, if we press that, we get 8 hours and 53 minutes. 8 hours, 53 minutes, and there's also 20 seconds. But because the question says to round this to the nearest minute, well, this is closer to 8 hours, 53 minutes rather than 54 minutes. Okay, there you go. That's the answer for question 10. Moving on to 11. The download time of a computer file is directly proportional to the size of the file. If a file of 1800 kilobytes requires 36 seconds to download, calculate how long it would take to download a 3000 kilobyte file. So we're having a look at two things, which is the download time and the size of the file. Okay, so maybe what letters we can use is T and S, maybe, okay, for time and size. So for part A, you use lowercase t for time equals K times the size of the file, so let's just say it's S, okay? I'll just make a capital S for now. So we have to substitute in some piece of information regarding that. So the size of the file was 1800 kilobytes, whereas the time taken to download that was 36 seconds. So we'll put that as T, and that is the size. So 36 seconds equals to K times 1800 kilobytes. We'll divide 1800 over, so that 36 divided by 1800 equals K. 36 divided by 1800 is simply 0.02. Okay, so T is equal to 0.02 S. And now we're asked to find out how long it would take to download a 3000 kilobyte file. So we can substitute that as S in there. So T would equal to 0.02 times 3000, which is equal to 60 seconds. So it would take us 60 seconds to download that 3000 kilobyte file. Question B says the size of the file that requires 80 seconds to download. Okay, so if we keep downloading at a constant speed of whatever it is, then what kind of size can we download? Well, let's find that out by writing our formula first. And we'll make a substitution of 80 seconds as capital, it should be T, okay, as our time. So in 80 seconds, what is the size of the file that we can download? How much can we download, actually? So we can divide 0.02 over to the other side. Okay, we can put it over 0.02 if you want, like this. And that's equal to S. So 80 divided by 0.02 is going to be 4000 kilobytes. Okay, which is also written as KB.